Hello everyone, my name is Shawnee Vu and welcome back to another video. This is week 6 and we'll be going over more on large language models. So what we'll be talking about is how they work, what makes them so powerful, some of the key concepts behind their architecture. So some of these we've already gone over before, but then a lot of what the new stuff we're going to be going over needs a lot of context. So we'll be doing a little bit of recap first. To start off, large language models are designed to take in text and predict the next word. These models operate on fragments of words called tokens. At its core, the input text is first broken down into tokens, which are often words or pieces of words. The model then represents each word's meanings in context as word vectors. For example, in the sentence, the customer asked the mechanic to fix his car, it is ambiguous whether his refers to the customer or the mechanic. The goal is for the final layer of the network to output the hidden state for the final word that includes all the necessary information to predict the next word. Machine learning models do not understand text directly. They understand numbers. Therefore, text needs to be converted into numerical representations. This is achieved through a process called tokenization, where text is broken down into smaller units called tokens. Like I said before, tokens are often words or pieces of words. Each token is then associated with a high dimensional vector called an embedding. These embeddings capture the meaning of the word. For example, the word king can be represented by a vector that encodes the attributes such as authority, wealth, and gender. Static embeddings have a problem where they can only capture one meaning of a word, but many words have different meanings based on context. For example, the word track can either mean the physical train tracks or the action of tracking a package. To counteract that, we use these things called contextual embeddings, which pretty much just capture the meaning of a word based on their surrounding context. Now, looking into transformer architecture, we can see that it consists of two main components, being the encoder and the decoder. The encoder takes the input sense and generates contextual embeddings for each token. It aims to understand the context of each word by considering the surrounding words. The decoder takes the contextual embeddings from the encoder and predicts the next word in the sequence. In tasks like language translation, the decoder starts with a special token and generates a translated sentence word by word. The two components work in conjunction to generate a coherent answer for the large language model. The encoder generates the contextual embedding, which is then fed to the encoder, which is to the decoder. Then the decoder predicts the next word. To keep it short, in terms of most languages, the order of the words matter. Transformers process input sequences in parallel, unlike recurrent neural networks that process words one by one. To account for the word order, positional encoding is used. Pretty much, this process adds a vector to each word embedding to embed knowledge of its position inside of a sentence. This vector contains information about the word's location. The transformer uses math formulas to derive the positional embedding. Now, onto the newer information, the attention mechanism. The attention mechanism is a critical part of the transformer architecture, enabling the model to focus on relevant words in the input sequence. There are a total of three core components that make up the attention mechanism. First of which being the query, which represents what a word is asking for or looking for in the context. You might imagine each noun, like the word creature, asking a question. Hey, are there any adjectives sitting in front of me? The second of which is the key, which represents the description or the information that each word provides about itself. For the words fluffy and blue, each can answer, yeah, I'm an adjective and I'm in that position. And for our last one is the value. which represents the actual content or contribution that each word brings to the context. If a word is relevant to adjusting the meaning of something else, the value specifies what should be added to the embedding of that something else in order to reflect this. By calculating attention scores based on the query, key, and value, the model determines how much each word should influence the others, ultimately refining the contextual embedding. To capture different types of relationships between words, transformers use multi-headed attention. Each of these heads produces its own context-aware embedding. One attention head may focus on adjectives, while another focuses on verbs or pronouns. For example, the word dish in a sentence, one attention head might focus on adjectives like sweet or spicy, while another looks at the verb made. Each attention head has its own distinct key and query matrices, which are used to produce their own distinct attention patterns. By combining the outputs of multiple attention heads, the model gains a more comprehensive understanding of the input. There are all these added together using the corresponding attention patterns as weights. What this means is that each position in the context, each token, every one of these heads produces a proposed change to be added to the embedding of that position. After the multi-head attention block, the data flows through a multi-layer perceptron, or MLP for short. This is the simplest kind of neural network, which looks like a couple of matrix multiplications with nonlinear elements in between. The majority of model parameters live in the multi-layer perceptron. As for the function of multi-layer perceptrons, they enrich each token embedding by applying nonlinear transformations independently. The attention head applies linear transformations, and the multi-layer perceptron applies nonlinear transformations. This enables the models to learn complex patterns and higher order features beyond contextual relationships. Google DeepMind research suggests that facts and general knowledge are stored inside these multi-layer perceptrons. For example, the knowledge that Michael Jordan plays basketball. A superposition is a hypothesis that attempts to explain how models can scale surprisingly well and why are they hard to interpret. The basic premise for a superposition is that in an n-dimensional space, if you want to represent different features using directions that are perpendicular to one another, the maximum number of vectors you can fit in is n, the number of dimensions. Knowing this information, if we relax the constraints just a little bit and allow the features to be represented by vectors that are nearly perpendicular, we can dramatically fit more vectors. For example, if the vectors were between 89 and 91 instead of just 90 strictly. The theory of the superposition implies that individual features are not visible as a single neuron lighting up, but instead as a specific combinations of neurons. Training a transformer model involves feeding it vast amounts of text data and adjusting its parameters to minimize the error in predicting the next word. The model is trained on pairs of text sequences where the input X is a sentence and the output Y is the next word. The model is trained on Wikipedia, from the internet, and book corpus. The training is self-supervised, meaning no manual labeling is required. The model also calculates the error between its prediction y hat and the actual next word y, and adjusts its weights through backpropagation. This process refines the WQ, WK, and WV matrix. The cost associated with each example is determined by the probability the network assigns the next correct word. The negative log of that probability defines the cost. The training process is to tweak the parameters to minimize the cost, in which the goal of this entire thing is to find a minimum on the cost surface. So, what can we conclude from all this? Some of the key things to take away is that the objectives of large language models is to predict the next word in a sequence. Word embeddings transform the text into numerical vectors to capture meaning. The positional encoding accounts for the words in the order of the sentence. The attention mechanism allows for words to focus on relevant context. The multi-head attention captures different types of relationships between words. Multi-layer perceptrons allow this model to learn complex patterns. Encoders process input while decoders generate output. Training involves feeding vast amounts of data and minimizing prediction errors. And superposition might explain why these models can fit many ideas into a seemingly small space and why they scale surprisingly well. The ongoing developments in AI and machine learning continually push the boundaries of what these models can achieve. Also, training data sets do not require human labeling so that the models may scale on their own. As models get bigger, they can fit more ideas into a seemingly small space, like I've said before, and we are on the verge of AI that will save you time by being able to conduct hours worth of research in just minutes. That's all for my presentation. Thanks for watching. See you next time.